Welcome back to System Software. Any questions from last time about process basics? I know we went over a lot of command line stuff, kind of the basic idea of the process abstraction. Questions from last time? Okay, let's go over the homework. So first question, which might look familiar, is what is a process? Anyone? Or call it out? Running program, yeah, it's a running program. So how does that differ from a program?
It has
Anyone care to explain the difference between a program and a process or a running program? You can raise your hand or call it out. No one? What does a process have that a running program doesn't? Or what's one thing that it doesn't? Okay, so it has open files. Yeah, that's one thing. So the program doesn't have any currently open files, right? Anything else? Yeah, you had. Yeah. So it's the state of the machine. So if you remember from computer architecture or computer organization, when the processor has registers, it has a program counter or an instruction pointer that lists which line of code you're running, which line of machine code you're running. And so you can think of the process as the program code plus that state, the state of the running machine. You can think of as the process. That's why it's different, and that's why the operating system or the kernel gives you that process abstraction, gives you an ability to work with that, because that's how you actually get programs running and running concurrently on your machine. Okay, so process running program. All right, so how can I send the output of the find command to the input of grep for .h without having to create a file explicitly? And write an example of a bash command to do this. Any takers on this question? Yeah. You do a pipe. Yeah, exactly right. So if I want to pass the output of find to the input of grep, I can use a pipe. So I'm telling bash, the command line interpreter here, I'm telling it to run both of these programs, but take the output of the left program and passes that as input to the right program. That's a pipe. Questions about this from last time? Showed a bunch of examples of this from last time. Who actually tried to do this on their command? Like, I know not many people used it. Did anyone actually try to do this and use this on their machine? No? Okay, a little bit. Some people tried to do it. Yeah? Okay. Okay, yeah, so some people had actually used this. Okay, so that's how you do that. That's how you use a pipe. How can I run a program as a background process in Bash? There's several ways to do this. What's one way? Yeah. Yeah, you can just put an ampersand, and that will run it and immediately put it to the background. It'll detach it from the terminal. So you can see I don't have a command line prompt here. It looks like I don't, because that prompt is all the way up at the top of my history. All right, good. Another way to do it is to run the program. So I'm going to see if I can do this. Pass it to sleep. Hit Control-Z to pause it, and then you can use the BG command to put it in the background. Okay, number 4, how can I pause Emacs, in quotes, that is, put it in the background, and then bring it back to the foreground? How do we do this? So let's say I'm running Emacs. Here's a program we're going to look at. Whoops, that's the Windows version of Emacs. Let me do it on the command line. So here's Emacs. How do I pause it and put it in the background? Control-Z sends a signal to suspend it. And then how do I put it in the background? FG is foreground. That'll bring it to the foreground. So BG is background. That'll put it in the background. And yeah, all right, I think that's it. Any other questions on the homework? So kind of a practical tutorial on process management and redirection on the command line. All right, other questions about processes, the basics of processes, before we move on to today's lecture? Okay, let's get into process creation. So remember that to create a process in the Unix world, you first fork, which duplicates the process, including the running program. And then you call exec to replace that running program. So there are two steps to this. Fork duplicates the process, and exec replaces the process's program code. So here's an illustration from the Linux Programming Interface book. We've got a currently running program, program A. When we call fork, all the state that's in that process is effectively copied to a new process. So remember, what's the difference between a process and a running program? Or a process and a program? The process is a running program. So on disk in storage, that program is just a sequence of instructions. The process is the state of execution of that program. So whatever variables have changed, whatever that's going to be reflected in memory, whatever program counter the processor has, that is what position in the program is currently being executed, whatever open files you have, that's part of the state of the running process. And all of this information is effectively copied to a new running process. And at that point, both programs are nearly identical. They're going to perform the same sequence of steps effectively. Now, one typical usage of this is to run exec in the child in order to replace that process with a new program and run that new program. So the question is, how can we actually do different stuff in the child? So if it really is a duplicate of the process, including the same program, the same memory state, the same position in the program, the same program counter, how do we avoid both processes just doing the exact same thing? That'd be kind of pointless, right? If we just want the same program to run over and over concurrently. Well, the only thing that is different between the two processes is the return value of fork. If we look at the man page for fork, it says, on success, the PID, that is the process ID of the child process, is returned to the parent, and 0 is returned to the child. So remember, when you call fork, there's a new process that's created, and the return value of fork will be a different value depending on whether the process is the parent process, the original process that called fork, or the child process. And on failure, -1, just like lots of other system calls. So let's take a look at an example of doing this. So let me revert this. So let's just call hello world here. Okay, so what do we expect this program to do? Let's take a look at the sequence of instructions. So it calls sleep, waits for 10 seconds, then it calls fork, error handling if fork is -1. Then we call sleep again, and we print hello world. So let me take these sleeps out so we can see this run. So we just call fork, check the return value, and print hello world. What do we expect this program to print out? Well, after fork is called, this running program is duplicated. So there are two processes that are running all of the code after fork. And the code that's running after fork is hello world, printf hello world. So we expect to see hello world being printed out twice. And this is exactly what we see. We see hello world being printed out twice. Why is it that hello world, both of these processes are writing to the terminal? That's because the original process, simple fork process, as its standard output, it's the terminal. And part of the state of the process is the set of open files that process has open. So remember, with standard I/O, the system guarantees that there are 3 open files: standard in, standard out, and standard error. And when there's a fork, so this is the open files before fork. This is your file descriptor table. This is that FD value, that integer that gets returned by open. It's just an index into this table. That table gets copied to the child's file descriptor. So all of the same open files are present in both the parent and the child. So that's why when we call fork, both are printing out to the same standard out, because standard out has been duplicated for the child. And so both print to standard out. Okay, let's put these sleeps back in so we can actually see, using the PS command, these processes being created. So remember, the PS command lists all the currently running process in our current bash session. It's really, I think, the child processes in our bash session, or descendant processes. So let's recompile simple fork, and let's take a look. So the first thing that runs is sleep 10. I'm going to put it in the background. So sleep 10 runs, and we can see that there's a single process that's being run. After 10 seconds, we call fork, and we see fork has created a new process. So process 34 is still here, but we have a new process ending in 72. And now here we see hello world being printed out twice. These two processes are still running because of this subsequent sleep, but eventually they'll both terminate. Okay, so that's just running fork, and all the rest of the program is the same. All right, so how can we do something different in the parent or the child? Well, remember, fork returns 0 when it's the child, and the PID of the child when it's the parent. So fork returns a different value depending on whether we're in the parent process or the child process. So just like with any code, if we want the program to do different behavior depending on some input value, we can use a control flow statement, like an if statement. So here I can check whether, say, the return value is 0, and say we're in the child. But in the parent, we can print out the child's PID. So remember, return value is either 0 if you're in the child process, or it's non-zero or greater than 0 if you're in the parent process. So what do we expect this program to print out? We should see both print statements being executed. It's going to take 10 seconds to run. Let me put this in the background. So here we have a single process. After 10 seconds, we'll see 2 processes. So there's the 2 processes. Now the both processes resume here at the sleep statement. After the fork, there are 2 processes, and so it resumes executing here at sleep 10. And now we see hello from the child and the parent's print statement. So now keep in mind that both of these print statements have executed, but it's not the case that these have simultaneously been executed in the same program. The reason both are executed is because there are 2 instances of this program being executed. In one case, the ret val is 0, so only this branch is run. In the other process, only the second branch is run, only the else branch is run, because after the fork, there are 2 processes, 2 instances of this running program, and both of those processes run concurrently and resume execution right after the fork returns. And because this ret value is different in the two different programs, two different processes, one of the processes runs the first branch and the other process runs the second branch. So that's the kind of fruit fly, the simple example of using fork. Blur here.
I don't understand how, especially if the child may perform further actions, how there's not like conflicts between the programs, especially if it's like overwriting things that the other program was previously.
It'll just happen. So, so first of all, we have the process isolation guarantee. So the memory is copied. So the system gives you the illusion that you have separate memory space. So it's implemented with copy on write, so they won't violate each other's memory space. But they do share open files, and the file system just allows, concurrent writes to those files, and then they'll be all kind of mixed up. They won't be nicely merged. Parts of each line may be overlapping with each other. So the kernel will at least make sure that each write is atomic in the sense, each individual write, but it won't provide any concurrency control over all the processes together to make sure they're not overwriting what they're not supposed to. So there's a whole body of techniques. There's a class here as well on multi-process programming, so how you can enforce concurrency and atomicity of larger operations. But they'll just step on each other's toes with those files. Just like in our terminal, they both wrote to the same output, right? So if you don't want that to happen, or you want some control over when they write, there's all sorts of classic techniques like critical sections, semaphores. There's all sorts of techniques for doing concurrency. This doesn't. There's none of these solutions are baked in, but you have the ability to make processes and then basically implement your own, multiprocessor stuff. Yeah.
Just to clarify that, so this is a flaw of this system that is solved elsewhere.
Well, it's not really a flaw. It's like a design decision. So the process isolation is just for memory and the processor, but the file system is shared, and both can write to the file system. So if you want to, so it doesn't stop you from doing other forms of concurrency. So you can do other forms of communication and concurrency between these processes. But from the kind of process abstraction view, they're both independent processes with their own memory, their own processor, writing to a shared hard disk, a shared I/O channel, or shared I/O file, if that kind of makes sense. All right, other questions on fork? Now I think I have to re-record that part because I feel a little bad forgetting to record. Okay, let's look at a slightly fancier version of fork where we look at the output. I'll just take out this program here. So this is a version, basically the same program we had, but just stylistically a little different. So in this case, it's using a switch case statement to handle the return value. You'll see this a lot in the LPI book. It's just kind of a slicker way, a way to avoid using an if statement. Might be marginally faster, but it's just a slicker way to handle the multiple cases of the fork return value. So switch case works by looking at this integer value here, and then matching it against the list of cases here. The compilers can translate this not to branches, but instead to not to an if then else statement. Instead, they'll just branch directly using a lookup table to branch to these different cases. But anyway, just wanted to get you familiar with, because you'll see this a lot in the LPI book. So, but it handles all the cases kind of nicely in one neat package. So we have error code handling, we have the child case here, and we have the parent when it's not -1 and when it's not 0. Questions on this version of the program? It's almost identical to what we just had, except maybe for the specific things we were printing out. But it's almost identical to this version of the program. Questions on switch case, the switch case version? All right. Okay, so let's look at now exec. So what does exec do? Does it create a new process? No. What does it do? Yeah, replaces. Yeah, replaces the program, replaces the just basically the memory segment that's holding the program code, and restarts the program counter from the beginning of the program. So let's take a simple example of exec. Clean this up a little bit. Okay, so here I'm going to run a program called getPID. All this does is it prints out the current PID, process ID of the currently running program. So we just have headers to include standard I/O and the syscalls. And here I just call printf on the getPID syscall. So getPID is here. It returns a process ID, and it's always successful. It never has any errors, so we don't have to check any errors. This just returns the process ID. So the process ID is like what we see in this process table. This is the PID. It's the ID that the system gives to the currently running program, to the newly running program. Kind of like the inode number is a unique ID given to files. The PID is a unique ID given to each new process that gets created. And what creates the process? How do we create a process? Fork. Okay. All right, so this program is just exec. There's no fork here at all. It just calls exec. So here's what it does. It creates these new structures. Let me show you the documentation of this. So there's several versions of the exec syscalls. I think there's a place that lists these. Yeah, so there's several different variations of these. These aren't going to matter that much in this class. But the first one is always a path or a file. It's a string that gives you the location of the executable program. And then the second argument, I think in all these cases, is argv. So if you've ever wondered how or why argv, where that comes from, this is where it comes from. It's being passed to the exec call. So one thing you might notice here is that this C program, you're defining a function called main. But who calls main? Where does main get called? So you're writing a function here. And whatever's doing that call, we'll see this when we look at how a program gets executed, but there's a loader that kicks off the execution of the program, and there's a C runtime which eventually calls main, passing in this argv. But the source of these args is the system call. The Linux system call takes the path to the program and those arguments, and then they eventually get routed to your main method in the program that you wrote. We'll talk about that a little more when we get into the compiler section, how the back end of the compiler works, but this is where your args come from. And then the environment, if you remember briefly, I talked about the path environment variable. These are these kind of stateful variables that you can define for your entire terminal session. Don't worry too much about those. These will always be like empty if we use these syscalls. And for this example, all we really need to see is the program name. So we just call exec. We tell the kernel to start running this program, to replace the memory of this currently, whatever process is running, to replace that memory with the program code of this that can be found in this file. Questions on that? So all this does is sets the name of a program, calls exec, or sets the path to a program, calls exec on that path, and that's it. So here on success, this function never returns. Why doesn't it return if it's successful? What's that? Well, it's more maybe subtle than that. Why does exec VE never return? What does it do? Yeah, what is it?
There's nothing to return to.
There's nothing to return to. This program is no longer in memory. Those instructions have been effectively deleted and replaced with the machine code found in the program. So it reads this file in, this getPID program, effectively clears out the currently running program and replaces it with this new program. So whatever instructions you have after this, and that for that matter, all the instructions in that program, they're gone, they're out of memory. So there is nothing to return to here. Instead, what exec-v does is after this program is loaded into memory, it calls main effectively. It starts at the beginning of this program, which will eventually call main. Questions on that? I know it's like a subtle point, but it kind of illustrates what exec-v does and why you kind of need the system to do this, because you're playing with like the contents of memory. So call exec-ve. If it's successful, this getPID program will now replace this main method and this whole program in memory and just start executing from the top, effectively calling main. If it's not successful, it'll return -1, just like a lot of system calls. And so that's why to do error handling here, all we have to do is write our error handling code after exec-ve. Because if it's successful, it won't return. If it returns, that meant exec wasn't successful, and then we can do our error handling. Questions on this? Really annoyed at myself that I wasn't recording. I'm going to have to re-record it because there were good questions too. All right. Okay, so let's run this program and let's see what it does. So simple exec. Okay, so what do you expect to be printed out, if anything, by this program? Okay, so this, right? Simple exec PID. Do we expect to see exec-v, this P error? Not if it's successful, right? Anything else? Just simple exec? Good question. So we're running the getPID program, and that also prints something. So should we see that being printed? Yes, we should, right? So we'll see everything that's being output up to the call to exec-ve, and then once exec-ve is called, this program, this simple exec program will be effectively wiped from memory, and the getPID program will be loaded into memory and started at the beginning, and that program prints something. So we should see both the simple exec program's output and also the getPID program's output. So let's take a look. And voila, both are being printed out. And notice that they both have the same process ID. So it's kind of prove to you that exec is not creating a new process. It's just replacing a process's program. Yeah?
For your SHAR program before getPID, does it matter if that's at the top or as long as it's before exec-v, does it matter where it is?
This one?
Yeah.
Char program? Yeah, it's just a string variable that's being used for exec-ve.
So if you put it like after the first print statement, it won't affect
No, it won't affect it. Yeah, it won't affect it. Yeah, we could put this print statement anywhere above exec VE. Now, if we, just to kind of illustrate this, just to prove to you whether or not this is, anything is being executed after exec VE, what about this program? Should we see different output from this program? Or same output? Let's take a look. So same output, right? This print statement is not being printed out. Why? What's that? I heard someone say something. Why is it not being printed out? Yeah, the program, this program is no longer in memory. If exec is successful, it doesn't return and just starts running get PID. Yeah.
Why is the PID the same?
Because it's the same process. It's the same process.
It has the same process ID?
No, there's no duplication. So remember, exec doesn't do any duplication of the process. All it does, it takes the same run, because remember, what's a process? A process is a running program, and in like low-level terms, that's the program loaded into memory, whatever memory state you have, your settings and variables, whatever open files you have, whatever processor state you have, that's the running program. And exec doesn't change anything else. It leaves all of that the same. All it does is replace the program and restart it. I mean, also, zeroes out memory, restarts the processor. But it's like, it's like replacing the DNA in a cell. The cell is still there, but it has different code. So it has different behavior. So the process is this kernel abstraction, this data structure that's being maintained by the kernel. It's not strictly the program. It's something that has a pointer to or contains the program code. But it's this abstraction for managing multiple running programs on a system. And so exec is just a way to replace the current process's program with a new program. That's all exec does. So yeah, that's why the process ID is the same, because we have not created a new process. How do we create a new process? Fork, right? So what if we want to do both? What if we want to create a new process without destroying our current process? We want to keep that running, but we want to create a new process to run a new program. How do we do that? Exactly, fork and exec. We use them together. So this is exec with just a running ls. We can skip that one. But this is kind of the punchline here. So we can use these tools together to run both a new process and a new program in that process. So you can use fork on its own for doing some multi-process programming. But if you want to manage a system of different programs being run, like SSHD, bash, then fork and exec can be used together to achieve this. So let me show you an example of doing this. Okay, so a little longer, but I've just basically just combined the two previous programs. So again, our standard includes. Here is our switch version of fork, which we'll call fork, and then do the error handling. And without looking inside these cases, you just just as a little quiz, is case 0 going to be running in the child process or the parent process? Child process. And then this default, this is going to be running in the parent process. Questions on that? This is equivalent to just having an if statement. So before I had like if ret val, if 0 equals ret val, then do this. This is equivalent in behavior to what I had in the other instance of fork. And then inside the parent, we're going to print something out. So whatever our current program is, we're going to keep running that. And in the child, we just have a copy of that simple exec program. We just do the exec call. So here we're going to call ls in our child process, and we're going to just write some other code. We're going to just print something out in our parent process. So to reiterate, this program is going to call fork, which is going to do what? It's going to create a new process. So now we're going to have two running process that are running the exact same program. But once fork returns, there's going to be a different return value, so two different cases are going to run depending on whether we're in the parent process or the child process. The child process is going to run exec, running the LS program, and the parent process is going to run print. Got to print this statement out. Questions on this? So we're just combining the two system calls. Questions on this code? Yeah. Yeah.
I was still confused about how it's the same PID with the previous example we did. So it was like I thought that it replaces the new code, right? The code is replaced, but how did the exact and the exact function, like when we use exact, how did it even know what the PID was in the first place?
So again, so why is it the same PID and what is the PID? So whenever you call fork, so fork is the only way you can create a new process. Whenever you call fork, just like when you make a new file, the kernel issues you a new process ID and keeps track of that running program. But all exec does is just replace the code that's being run. So the process stays the same. It's the same running process, but you just swap out the code and start running that code. But it's reusing all of the kernel data, including the process ID for that executable. So it's akin to just calling a function, like calling another function in another program, kind of. It's like calling a main on another program in some sense. Other questions on this code? All right, let's compile it. Hopefully it compiles, because I did not try this one out yet. All right, what do you expect to be written out? What do we think we're going to see in this program?
LS and child PID.
Okay, we'll see the LS. So, well, the word LS, or what are we going to see?
Well, like the program of LS will run.
Well, it'll run, right? And where will it be output? Where will LS's output go? What's that? Standard out. It'll go to, it'll just copy this process, this fork exec program. It has standard I/O, has 3 files open. Those files will still be open in both of the processes. So LS will go to the same place that this parent process was going. Okay, so we should see LS being run, the output of the LS being run, or it should be visible in our terminal. And we should also see this printf statement, right? Just like with any fork. So let's see what happens. And there we go. So we see the parent is still running. We see inside the child process. And we can see here, to one of your classmates' question, which one runs first. So we actually see that this child process is a little delayed, right? A bash started resuming before the child was scheduled. That's the only reason you see, that the prompt's being printed out. But you can see we've got the parent is still running. That's this code here. And then we see inside the child process, that's in this program. And then exec is called. And once exec is called, the LS program replaces that process, starts running, and we see its output. And this is exactly what bash does. When bash runs LS, this is exactly what it does. Bash is still running. It's forked a new process, and it's called exec in that fork to replace the current program with LS. So I think I have a version of this with sleep, so we can see the actual processes. But questions on this code, question on its output. Okay, so here's another program that sleeps in the child. Oh yeah, so this is just so we can see, so we'll be able to see the child process, or so this one calls sleep instead of LS, and then the parent also sleeps, so we'll be able to see the process get created. So it does the same thing. It doesn't call ls, it calls sleep. So I'm going to run this in the background. And you can see here that we have two processes. One is called fork exec sleep. And the process, so this is the child process. It's been renamed to the program. The process has been renamed to the program. But that's all I wanted to show you with this. So you can just see that there are indeed two processes, and because exec was called this second process, this child process, which you can see the child PID here ending in 8.8. This is the child process ending in 8.8. Its name has just been replaced with the program name. But you can see that the two processes are actually running. Yeah?
Similar to the last question, so like when you have your program reset to like sleep or LS, it doesn't have to be like, as long as it's in the program and it's reached before the exec V will call it on, right? So like it doesn't have to be within the same case.
Do you mean the prog thing?
Yeah.
Yeah, this is just, there's nothing kind of systemsy about this. This is just normal C semantics. So as long as this prog variable is in scope, it's set somewhere in scope. And remember, when this fork happens, the memory is copied as well. So if, I've defined prog here, but if this prog were defined up here, or like PID is defined up here, both processes will have copies of that memory. But if you think of them individually, they just work like a sequential C program. They work the same way. Other questions on this code? Fork and exec, yeah.
With exec, is there ever a case where the memory for the previous program isn't enough to accommodate the new program?
Well, so it's the kernel that's managing the program memory. So certainly, yeah, if you ran out of memory somehow, ran out of like virtual memory somehow, which is kind of hard to do on 64-bit systems, but if you ran out of memory, the fork would likely just fail. There's probably even, I'm guessing there's even so there's like an eNoMem error for fork. So yeah, you could run out of memory. This is one of the things that a fork bomb can do on certain systems. Is that it can run out of memory, but yeah, it'll fail. So the parent won't fail. The parent's memory won't be taken away, at least not conceptually. But the kernel will, when it tries to create a new process and allocate memory for it, it may say, I don't have enough memory for a new process and fail. But yeah, it's good, subtle question. Other questions on this code? All right, so that's fork and exec. That's how you create a new process and a new running program. And I'm going to re-record that section.